In this video, we will go over the dot product, cross product, and triple scalar product. We'll see how to compute them and their geometric implications. In the previous video, we learned about scalar multiplication, which was a scalar times a vector. Now let's see how to multiply a vector by a vector. There are two different ways called the dot product and cross product. Let's start with dot product. This operation multiplies two vectors and returns a scalar. Look at this example. To perform the dot product, we simply multiply each component, then add them all together. Let's look at the dot product between these two vectors. The dot product is also equal to the multiplication of their magnitudes and the angle between them. This formula can be used to find the angle between the vectors. To do so, first let's solve for theta. After you calculated the dot product and the magnitudes of the vectors, you put it back into that equation, and we see that for this example, we get an angle around 29.7 degrees. Let's see how the dot product changes based on the angle between them. We see that when they point in the same direction, the dot product is the greatest, and when they point in opposite directions, it is the lowest. Also, when the vectors are 90 degrees, the cosine of 90 degrees is 0, so the dot product is also going to be equal to 0. We can observe that the dot product measures how aligned two vectors are. You can pause and briefly look over these properties for dot product. Now let's move on to the cross product. The cross product multiplies two vectors, like the dot product, but now it returns another vector. Also notice that the return vector is orthogonal to the other two given vectors, meaning that it's 90 degrees to both of them. Let's try it and take the cross product between the red and blue vectors here. To do so, we have to create a 3x3 matrix with I, j, k on the first row, and red vector on the second row and blue vector on the third. Then we need to find the determinant of this matrix, which will yield another vector, and that is the cross product. I will show how to find the determinant of the matrix in lesson 4 of this playlist. Also, for the cross product operation, the order will matter. So V1 cross V2 is not the same as V2 cross V1. But the only difference between them is that they will point in opposite directions, but they'll have the same magnitude. Besides computing the cross product by finding the determinant, you can also use the right-hand rule, where you point your fingers in the directions of the given vectors V1 and V2, then stick out your thumb. The direction your thumb points in will be the direction of the resultant vector. The cross product returns an orthogonal vector. The magnitude of that vector is equal to the multiplication of the magnitude of the vectors and the angle between them. When the angle between the vectors is 0, sine of 0 is 0, so the cross product is also 0. When the angle is 90 degrees, the cross product will be the greatest. An interesting fact about the magnitude of the cross product is that it is equal to the area of the parallelogram formed by the initial vectors. And this makes sense when you consider the cross product is 0 when the angle is 0, and also the area of the parallelogram is 0 when the angle is 0. Usually the cross product is only defined for 3D vectors, but some textbooks say the cross product between two 2D vectors is the determinant of the 2x2 matrix formed by the 2D vectors. The result would be scalar in this case, but that scalar would still represent the area of the parallelogram formed by the 2D vectors. You can look over these properties of the cross product. Now let's look at the triple scalar product. This operation has both the dot product and cross product. To compute the triple scalar product, you would find the determinant of the 3x3 matrix formed by the three vectors. This time, the result will be a scalar. The result represents the signed volume of the parallelepiped created by the three vectors, as you can see in the image. I say signed since the result can be negative, but if you take the absolute value, then it will equal to the volume. Let's try to see why the triple scalar product results in the signed volume of the parallelepiped. First, we realize that the volume of the solid is equal to one of the bases times its height. So let's take the cross product of v and w and call the resultant vector t. Note that the magnitude of t is equal to the parallelogram formed by v and w, which is one of the bases. Then let's write out the dot product between u and t. Next, we will need to find the height. To do so, let's take the cosine of the angle between u and t, which is equal to height divided by the magnitude of u. To be more clear, we're finding the cosine of this right triangle here. Then let's solve for h and put it back into the original equation. We can see that the original triple scalar product is equal to the magnitude of t times h, which is base times height. Remember that the triple scalar product yields a signed volume, so the formula for the volume is just the absolute value of that. And this absolute value sign also makes it so you can take the triple scalar product in any order. In this video, we went over 3 new concepts. It may seem like a lot, but if you understand how to compute them and the information on this slide, you will have enough understanding to move on. In the next video, we will discuss projections.